Hi guys, it's 7:42 p.m. and now we have finished our final layout. So this is actually the layout of the ring oscillator, and yeah, this is actually the final. Maybe I need to modify a little bit, but as you can see here, all of the block has been integrated in one top level, we say, and yeah, this is the final result. And as you can see, this sort of like horizontal line is basically the metal layer, and you can see several in the vertical is actually the metal 2 we call the yellow one, and the blue one is the metal 3, and metal 1 is the silvery color you can see here, and this is the gut ring. And these components are transistors. As you can see, it has drain and source. Basically we have finished. This is the ring oscillator, and this is the schematic, right? And we have this 5 stage. So this is the 5 stage, right? This is the 5 stage, quite compact with transistors. And yeah, let me show you this is the biasing circuit, right? The biasing circuit. So the biasing circuit is basically to bias the oscillator. And why we need to bias the oscillator? Because we want our transistors to operate in specific cue point or operating point, right? Maybe we want operate between triode regions or saturation region. So that's why we need to have this biasing components, right? So we have about 30 transistors in this biasing circuit, and this is all PMOS, right? And this is the gut ring. So gut ring is basically to provide the uh, power source to the transistor, and also to act as a to protect or to guard the transistors, all of them, right? And as you can see here, so as you can see here, we actually arrange the transistors in 2 rows. This is called basically common centroid matching, as I already explained last time. So we want to ensure that all the transistors as similar as possible. And in order to do that, there is a specific arrangement we need to do. So this one is actually common centroid. There actually another technique called interdigitated, and also the quad cross quad cross quadding. Yeah, cross quadding. And I'm using the common centroid one. So basically, actually, if you see the arrangement, it looks like this. Where is the schematic? And can you see here when I click this? So this is at the middle. This is the reference current mirror reference. So at the middle, it always at the middle, and this is the one that copy the reference current. So you can see this is the dummy. So you can see that common centroid is like you have one common center or center of gravity, such that when you fold this block, so it is like the mirror image of each other, right? So this one and this one, and this one with this one, and the dummy is at the end. So you can see when you fold the block, this and this will be met. They will meet each other, and it acts like a mirror image. That's common centroid. Okay, so that's biasing. um, okay, and then this is actually our inverter. So our inverter here is just composed of NMOS and PMOS, that's all, right? But in the top level, we combine into 4 transistor inverters here. So actually we combine this one, we just combine 1 2 3 4 5, sorry, 5 inverters we combine, right? So this one is only one, but we need to duplicate them. into five, and this is the five stage. So it looks messy here, but oops, yeah, this is a five stage. And okay, this is the main oscillator. So of course, ring oscillator is a circuit that provide synchronization to the digital or logic circuits. So it will be connected to the next logic circuit. So of course the ring oscillator is not functioning by itself. So it's like a supporting circuit, right? And yeah, this is our main block. So it looks quite squarish here. So that's our objective, to make it as square as possible, because you need to save space and so that you can fit in as many as possible components inside, right? Okay, yeah. So actually, overall, I'm not done yet because this is just the layout. Okay, this is just a layout, and we need. Okay, of course, I already done the analysis, the DRC, the design rule check, and also the LVS, the layout versus schematic. All of them, both of them, clean. So, which means that I am quite good in the good position now, because everything goes well as intended, even though I face somehow a little bit error at first, but yeah, at the end I managed to uh, settle everything up. So that's quite a good news. Yeah, everything is good. So LVS, compare pass, DRC, and extraction results clean. We are good to go. But the next verification is basically this one, the LPE, or the parasitic, right? So yeah, I'm going to do this next. But what is parasitic actually? So because as you can see here, this is metals, metal 3, metal 2, and metal 1. So you need to know that in electronics, so we have when we have metals or conductor, so we have two properties of that we can see, which is the capacitive properties and also resistive properties, right? Capacitive and resistive properties. So all of the metals that we have has these properties, right? So for the parasitic, we have two, which is capacitive parasitic and also resistive parasitic. So what is resistive parasitic? So because we see these connections, let's say let's take this simple connection, this to this. So of course current will flow, right? But this, because the properties of the materials of the metal, so there will be an IV drop, sorry, IR drop. There will be an IR drop. So let's say here is supplying 10 volt. So current will flow, right, from higher potential to lower potential. Let's say this is 10 volt, this is lower potential. So it will flows here. But along the way, actually, the potential will drop. So let's say this is 10, this must be lower than 10, let's say, because this has resistance, right? Even though it's not resistance, but this has resistivity properties which induce resistance. So here 10 volt, this might be, let's say, 9 volt. So the drop is about 1 volt, right? So of course this is not ideal. So that's why there will be a parasitic resistance. And what about the parasitic capacitance? You remember what is capacitance? So let me draw something. I want to draw paint. Paint. Right. So what is capacitance actually? So capacitance, when you have, let's say, you have two parallel plate, and this is conductor, metal and metal. When you have this metal and metal, there is a current flow, right? Let's say there is a current flow. So of course, this metal will act like a capacitor. So capacitor, so when you connect this to source, let's say volt, this, there will be a accumulation of charge here, accumulation of negative charge here, so same potential but different sign, so there will be an electric field. Okay, and what is the voltage across this parallel plate is actually when it already uh, fully charged, so the uh, charge accumulated is actually C times V. So V, when it is fully charged, C is the capacitance, and Q is the amount of charge accumulated, right? So this is capacitance, capacitor. But this is not capacitor. This is just a metal, but it can act like a capacitor. We call parasitic capacitor. And as you can see, this is a metal, parallel metal plate, and this is parallel metal plate. So of course there will be a supply current source. Sorry, I mean there will be a current flow. There will be a source, right? So when that happens, then there will be an accumulation of charge here. Accumulation of charge here. So there will be a sort of like electric field induced. Okay, so that's how the parasitic capacitor arises, right? So that's why this is very important. We need to make sure that our circuit or ring oscillator has as low as possible parasitics. Okay, so that's why we need to run this. After that, then we will set up our test bench, and we are going to check our parasitic here, and we are going to do the Monte Carlo to make sure that uh, our, let's say, our chip or our circuit is within the spec, within the 5 sigma that we wanted, right? That the client wants, right? So it depends on the manufacturing, how many sigma that they want, right? And that's the Monte Carlo. And for the corners, we are going to check the worst case corners, like let's say the our circuit, we want the circuit to operate ideally at 5 volt, right? But of course, uh, it's not always 5 volt, because the supply may change, may vary from, let's say, 4.3 to 5.3, let's say, volt. So even though in this worst case scenario 4.4 volts, we want our circuit to still operate very well. So that's why we run the corners to ensure that our circuit still works even though in the worst case scenario, right? So that's the significance of this circuit. So that's overall about it. Yeah, so it's already 30 minutes I'm talking, yapping. So yeah, I will update when I finish all of them. Yeah. So till next time, cheers.